Hello everyone and welcome to this week's video. Today we're going to be learning about ideal air-fuel ratios. Now an ideal air-fuel ratio is a ratio of air to fuel so that after combustion you have no oxygen left over and you have no fuel left over from the combustion process. So you may have already heard before that this is about 14.7 to 1. But where does that number come from? The 14.7 parts air to 1 part of fuel. So what you've got happening in combustion is you've got gas and air going into the cylinder, and then you're going to have coming out of your exhaust, you're going to have carbon dioxide and water. So gas will be represented here by octane, which the chemical formula of is C8H18. Air is primarily nitrogen and oxygen. So for the purposes of this video, we're just going to say that air is 79% nitrogen and 21% oxygen. Now I know it's more like 78, 21, and then 1% argon and 0.03% carbon dioxide and whatever, but point is for this video, for simplicity, we're just going to do 79% nitrogen, 21% oxygen. So when you divide 79 by 21, you get about 3.76. So for our one unit of octane, C8H18, we're going to add to that our units of air. So air is going to be, for every one oxygen molecule we have, we're going to have 3.76 molecules of nitrogen. So that comes from right there. So we don't know what's going to be in front of that. We're going to balance an equation here. So this is going to give us carbon dioxide, CO2, and I should draw that a little smaller so we can fit a number in front of that, plus water, H2O. Okay, so to balance an equation, it's pretty simple. All you want to do is just get the same parts of both on each side. So you've got equal carbons, equal oxygens, equal hydrogen, and equal nitrogen. So in order to do this, we'll just start with the carbons. We've got 8 carbons here, so we know we're going to have 8 carbons there. We've got 18 hydrogens here, so we know we want to have 18 here. 9 times 2, 18. So now we want to balance the oxygen here. So we're going to have, let's see, 2 times 8, we've got 16 plus 9, that's 25. So we've got 2 here, 25 divided by 2, that'll give us 12.5. We've got 3.76 nitrogens, and that should give us, I believe it's 47. That number doesn't really matter anyways, but point is, balance the nitrogens. Okay, so now that we've got this balanced out, we want to see what's the ratio of air to fuel that's going to give us the exact results we want in the exhaust. So we're going to take our molecules of air that we have. We've got 12.5 times the amount of oxygen. So oxygen has an atomic weight of 16, so that'll be 16, and then there's 2 of them times 2, plus we're going to add to that 12.5 times 3.76. Nitrogen has an atomic weight of 14, and also there are 2 of those. Multiply that by 2. So on the bottom of that, what we've got going on is C8H18. So you've got 8 molecules of carbon, atomic weight of 12, plus 1 molecule of hydrogen, atomic weight of 18. So when you multiply all this out, you get about 1716 on the top and 114 on the bottom. You divide that and you get an air-fuel ratio of 15 to 1. Now you're asking yourself now, okay, 15 to 1, that's not 14.7 to 1, but take into consideration we did have a couple assumptions. One being that air was 79% nitrogen and 21% oxygen. The other being that gas can be perfectly represented by octane, which is C8H18, which it cannot. Gasoline is actually quite a big mixture of different hydrocarbons, all of which having different characteristics and ultimately different air-fuel ratios. So a more realistic, ideal air-fuel ratio is going to be about 14.7 to 1. So that's where that number comes from. If you have any questions or comments, just leave them below.